हेलो स्टूडेंट्स, आज का टॉपिक है एसिड बेस एंड बफर। सो पहले हम पढ़ेंगे एसिड क्या होते हैं। एसिड्स आर नोन सिंस ages past previously and still acid is described as substance which react with base to give salt and water. Acid turns blue litmus paper red. They react with metals liberating hydrogen, and also acids react with carbonates liberating carbon dioxide. Let us study some theories which describe the definition of acid. First theory is Arrhenius theory. The theory describes acid or base as substance which on dissolution in water dissociates forming ions. Then an establishment of equilibrium between ionized and unionized molecules takes place. Arrhenius described an acid as a substance which when dissociate in water gives hydrogen ions. For example, HCl, when it is added into water, it dissociates into H positive and Cl negative. Next example is acetic acid, which also gives H positive ion and acetate ion. As per Arrhenius, base is a substance which, when dissolved in water, yields hydroxyl ions. For example, sodium hydroxide, when added to the water, it gives sodium ion plus hydroxyl ion. And next is ammonium hydroxide ion, which gives ammonium plus hydroxyl group. Here sodium hydroxide and ammonium hydroxide dissociate to give the positive and negative ions. Both acids and base undergo neutralization reaction. The neutralization reaction results in forming water and salt. For example, sodium hydroxide plus HCl. Sodium hydroxide is a base, HCl is an acid. When both are mixed, it forms NaCl, which is a salt, and H2O, which is water. Limitations of this theory. The theory defines acids and bases in terms of aqueous solutions and not in terms of substance. The next limitation is the basic substances without hydroxide ion in their structures are not explained by this theory. Third limitation is the theory has no explanation for acidic and basic properties of substances in non-aqueous solvent. Next theory which we are going to study is Bronsted and Lowry theory. The theory suggests that an acid is a substance that can donate a proton and base is a substance that can accept a proton. Thus, acid is a proton donor, base is a proton acceptor. As per Bronsted-Lowry theory, an acid is equal to H positive plus base, which is also conjugate. For example, HCl dissociate into H positive plus Cl negative, which is conjugate. Next is Lewis theory of acid and base. Though Bronsted-Lowry theory is widely accepted, but it failed to take its consideration many other acids which do not have proton or which can transfer proton. In 1923, G. N. Lewis proposed a definition of acid and base. The definition proposed by Lewis is in terms of electronic structures. The theory states that an acid is a molecule or ion that can accept a lone pair of electrons, and a base is a molecule or ion that has a lone pair of electrons that is denoted. So acids and bases, what are these exactly? The exact definition of acids and bases depends on the particular system involved, or in better sense, it depends upon the actual acid-base reaction which taking place. The Bronsted-Lowry concept, which was developed independently by J. N. Bronsted and J. M. Lowry in 1923. As per this definition, a Bronsted acid ionizes to produce a proton and the conjugate base of the acid. For example, HA is an acid which breaks down into H positive plus A negative conjugate base. HCl, which breaks into H positive and Cl negative ion, which is a conjugate base. Bronsted bases are anions or neutral molecules. The chemical species formed when a base accepts a proton is regarded as the conjugate acid of that base. Hard and soft acid base concept. This concept provides a quantitative view of various factors affecting the stability of acid base complexes. R.G. Pearson developed this concept. This concept is also known as Pearson's principle of hard and soft acids and bases, or Pearson's HSAB principle. HSAB principle categorizes acids and bases as per their properties of charge, size, and polarizability, etc. According to HSAB principle, hard acids are electron acceptors having high positive charges, relatively small size, and unfilled valence shell orbitals. This provides high electronegativities and low polarizability to these species. Soft acids have low positive charges, relatively large sizes, and filled valence shells orbitals. These properties impart high polarizability and low electronegativity to the species. For example, hard acids H positive, lithium, sodium ion, potassium ion, magnesium ion, calcium ion, and aluminum ion. Soft acids are copper ion, silver ion, Orus ion, mercury ion, iodide ion, bromide ion, iodine, bromine. Border lines: ferrous, copper, zinc 2 positive, lead 2 positive, strontium 2 positive, strontium 2 positive. Hard bases: they possess high electronegativities, are reduced easily, and have low polarizability and stable valence shell structures. Soft bases are less in electronegativity, easily oxidized, have got empty low lying orbitals, and high polarizability. For example, hard bases: H2O, hydroxyl ion, fluoride ion, phosphate ion, and sulfate ion. Soft bases: iodide, cyanide, and hydride. Borderlines: bromide, they sulfide aromatic amines, pyridines. It is concluded that the most stable adducts are formed between hard acids and hard bases, and or between soft acid and soft bases. Next topic which we are going to discuss is buffer solutions. What are buffers? Buffer solutions are solutions of standard pH. They are used in various types of tests which requires adjustment to or maintenance of a specific pH. Carbon dioxide free water should be used for preparing buffer solutions. They should be stored in chemically resistant glass stoppered bottles of alkali free glass and used within 3 months of preparation. Any solution which has become cloudy or show any other evidence of deterioration should be discarded. Standard buffer solutions have various pH range between 1.2 to 10. They are generally prepared by proper combination of 0.2 normal HCl and 0.2 normal sodium hydroxide, and also by using 0.2 molar solution of potassium hydrogen thalate, boric acid, potassium chloride, and potassium dihydrogen phosphate. These are described in pharmacopoeia and other official books. The examples are acid thalate buffers, which is having pH 2.2 to 4 to 50 ml solution of potassium hydrogen thalate is added the specified volume of hydrochloride acid, then water is added to make the volume to 200 ml. Next example is hydrochloride acid buffer. It is prepared 50 ml of 0.2 molar potassium chloride solution in 200 ml volumetric flask, and specific volume of 0.2 normal HCl is added to make the volume of 200 ml with water. Next is alkaline borate buffer having pH 8 to 10. It is made 50 ml of boric acid potassium chloride solution. The required volume of sodium hydroxide solution of known strength is added. Then pH is adjusted to required value and volume is made up to 200 ml with water. If a small quantity of HCl is added to pure water, there arises a rise in H positive concentration, hydrogen ion concentration. In this same way, if NOH is added to pure water, the hydroxyl ion concentration rises. These changes occurs because water cannot neutralize the traces of acid or base present. In other words, it has no ability to resist changes in hydrogen ion concentration or pH. Now there are certain substances or combination of substances in aqueous solution which possess the ability to maintain a desired pH at a relatively constant level. This constant level is maintained even with the addition of a material that can change hydrogen ion concentration. Such as substances or combination are called as buffers. The ability of buffers to resist changes in pH is buffer action. The efficiency of substances to act as buffers or buffer action is called as buffer capacity. Therefore, a buffer solution is a system, usually an aqueous solution, that can resist changes in pH upon addition of small amount of acid or base. Use of buffers: preparation of injections and ophthalmic solutions, pharmaceutical tests and assays which need adjustment and maintenance of specific pH for analysis.